Time value of money, a comprehensive review. A dollar saved is a quarter earned. I like this quote by John Ciardi because it helps us remember what the essence of time value of money is, which is the notion of interest, in particular compound interest. So that if we save a dollar, for example, deposit a dollar in a simple interest bearing savings account, and we let some time go by, we can earn some additional cash. Let's define some variables. These are some starting variables that are relevant to time value of money. The first is P sub 0, or the present value. This is known as the principal at time 0, the principal amount of funds at time 0. Next, let's talk about P sub t, or what we might later call a future value. This is some future sum of money that we will have at time t. N would be the number of compounding periods, and I would refer to the interest rate. It's important to note that variable names for interest and time may differ. Be able to adapt to these differences. For example, you might be familiar with the use of R for the interest rate. Okay, so what we want to do is invest P dollars for 1 year at I%. Again, let's think about simply depositing some money into a savings account and letting it earn some interest. How much would we have at the end of the year? We will have the original P0 that we started with, plus the additional amount we earned in interest over the year, or I% of P. Mathematically, we can write this as we have shown here. P1 is equal to P0 plus P0 times I. Or we can rearrange the equation and we could pull out the P0 and multiply it by 1 plus the interest. So that in general, we can say that the future value, or the amount we will have at the end of the first year, will be equal to the amount we started with, in this case P0, multiplied by a factor of 1 plus the interest rate for that year period. Let's leave the P dollars, the P1 in the account for one more year at I%. And let's see, well, how much would we have at the end of the second year? Following the same format that we did in the previous slide, we could say that the amount we'd have at the end of period 2, or P2, would be equal to the amount we started with in that period, P1, times the interest that we earn in that period, which is I times P1. We could substitute into this equation, we could substitute for the P1 that we found in the previous equation. And I have done so here in this line. Here we see that P2 is equal to P0 times 1 plus I, plus P0 times 1 plus I times I. Now we could reduce that equation and simplify it by finding this equation here. P2 is equal to P0 times 1 plus I squared. Now, if you're not sure how I jumped from steps 2 to 3, please click on this orange box and it'll give you the detailed description of how we moved from step 2 to step 3. So in general, what we can say is that if we want to know the value, or the future value of at any period in time n, we can find that by simply taking the initial value P0 and multiplying it by 1 plus I to the end. Now what I'm going to do here, as you can see, is that I have changed my terminology from the P sub n and P sub 0 notation to using the more familiar to Excel and to financial calculators, using the terminology future value and present value, as we just defined a few slides ago when we defined our variable. Now let's take a look at an example to help clarify this for us. Let's say we want to invest $25 for 5 years at I%. What is the value of our investment at the end of the 5 years? So we're looking to solve the equation of future value, that is future value of a lump sum. If we'd use the equation that we just derived in the previous slide, we would take our $25, the initial amount, and multiply it by 1 plus the interest, in this case 6%, compounded out 5 periods because we're talking about 5 years or 5 compounding periods. If we want to look at that pictorially, what we're trying to see is if we were to compound out that $25 that we get in time, or that we have in time 0, and find what its value in time 5 is, we would simply use the equation that we have listed here. Now we have several ways that we can solve this problem. We could use our y to the x key. That is that we could punch into our calculator 1.06. Using the y to the x key, we can raise that sum to the 5th power. Another way is that we could employ our financial calculator. Here we're going to have a several-step process where we're going to enter various inputs into our calculator and ask it to compute for us the future value. The inputs that are relevant for this problem are, in fact, the present value, which is going to be 25, the interest rate, which is going to be entered as 6, and note here that interest is entered as a percentage, not as a decimal. And n being the number of compounding periods, we'll enter a 5 for, and we'll compute our future value at 33.46. Now you may ask yourself the question, why do I have a negative 25 for the present value? Our calculator needs to understand the difference between inflows and outflows. If we are to pay out $25 or deposit $25 into a bank at time 0, we would receive back in time 5, at the end of the 5 years, we would receive back $33.46. Another way to solve this is to use the future value of interest factor tables. These are typically located in the back of financial textbooks. They can be found on websites and so forth. Again, the title of the table would be a future value interest factor table. And what it does for us is it calculates various interest factors for a lump sum calculation with various interest rates and various ends. So if we were to look at that table and look and see what the interest factor portion is, that's the 1 plus I to the n, in this case 1.06 to the 5th, we would find that that would be equal to 1.3382, that which we could multiply by our present value to get the future value. The fourth way is to employ the use of an Excel spreadsheet. What I have done here is I have shown you what the formula looks like in Excel. If we designate certain cells for present value, interest, and n, we can write in a formula into Excel that designates what the future value of that lump sum would be. In this case, $33.46. So the answer to our question, no matter which way we solve it, we should come up with the future value to be equal to $33.46. Now again, you'll note here that I have entered the present value as a negative, as Excel works much like a financial calculator, needing to know the differences between inflows and outflows. Now, time value of money is all about interest, specifically compound interest. So let's start by talking about some different types of interest rates that are both relevant to time value of money and our general knowledge. We will talk about 3 different types of interest rates: the annual percentage rate, or the APR, the periodic interest rate, and the effective annual interest rate. The annual percentage rate is the nominal or stated interest rate. These are the interest rates that you find in any financial contract or obligation, such as a credit card bill or an auto loan statement. You would find the annual percentage rate. The periodic interest rate is the rate per period. For example, the rate per day, per week, per month. Here we would see that the periodic interest rate is calculated by taking the annual percentage rate and dividing by m, where m is equal to the number of compounding periods per year. So if we're talking about a daily compounding scheme, we would have m being equal to 365. For weekly compounding, m would be equal to 52. For a monthly compounding scheme, m would be equal to 12, and so forth. The effective annual rate, or the EAR, is what we would consider the true rate of interest when we take into account compounding. It is the annual rate which causes the present value to grow to the same future value as under multi-period compounding. Now, I want to point out a very important point here, that when we are discussing our time value of money calculations, the interest rate that will always be used is the periodic interest rate, the rate per period. Now let's take a more in-depth look at the effective annual rate. That is, again, the true rate of interest. Once we've taken into account the effects of compounding, what is the actual interest rate we are either receiving or paying? Let's do this by way of example. Suppose we have a passbook savings account that advertises an 8% APR compounded quarterly. Okay, so our interest rate that we'll use in our time value of money calculations, or the I, is actually going to be the periodic rate. In this case, it's going to be 2% per quarter. We take our 8% APR and we divide it by 4, the number of compounding periods in this compounding scheme, in this quarterly compounding scheme. If we start again with our P sub 0, as we did initially in our talk, let's say, for simplicity, let's start with $1 and see what is it we're going to have after each quarter goes by. Well, after the first quarter, we would have $1 too. $1 times 1 plus the interest rate. Again, the interest rate being the periodic interest rate, or 2%. After the second quarter, we would have 1.02 times 1.02, or 1.02 squared. Okay? And after the fourth quarter, we would have 1.02 raised to the fourth. This is all employing the knowledge that we have just talked about in terms of future value. In this case, the amount we would have after the full year had gone by would be 1.0824. So the interest rate that we actually earned over this time period is 8.24%. Now let's put this into an equation that we can use on a regular basis. The effective annual rate can be calculated by taking 1 plus the APR and dividing it by M, in other words, the periodic rate, raising that sum to the nth power, and then subtracting 1. So for the numerical example that we used, we would have, again, of course, come up with the 8.24% once we have inputted those variables into our equation. It's useful to know when each of these interest rates are used. We've already talked somewhat about it, but let's summarize. The APR is written into contracts. It is quoted by banks and brokers. It is not used in calculations or shown on timelines unless compounding is annual. The APR over M, or the periodic rate, is used in calculations and shown on timelines. So this is the key rate that we're going to be using in our time value of money calculations. And the effective annual rate is used to compare returns on different investments with different compounding patterns. So if we were trying to assess the interest rate on one investment scheme that had monthly compounding as compared to one that had daily compounding, we would need to calculate the EAR, or the effective annual rate, to accurately assess the interest rate differences. The EAR is also used for calculations if dealing with annuities where payments don't match the interest compounding periods. Let's go back to our time value of money calculations. Now that we've gathered ourselves together with interest rates and understand fully the different interest rates that we should use in our time value of money calculations. Let's look at the opposite of compounding, or future value, that we've already discussed, and looked at something called present value, or the present value of the lump sum. Let's suppose that someone offers you $33.46 and promises to pay you in 5 years. The question that you should ask yourself is, what is that investment worth today if interest rates are currently at 6%? So if we want to look at this on a timeline, what we're asking here is that if we have $33.46 in period 5, what is that equivalent? What is the equivalent value in time 0? How much is that worth in time 0 after we have discounted or backed out all the interest that we would have earned in that intervening time? Now to solve this, let's first recall our future value formula. We stated that the future value would be equal to the present value times 1 plus I to the n. So if we would like to solve for the present value, we could simply rearrange the equation and solve for present value. In this case, it would turn out to look like this. Present value would be equal to the future value divided by 1 plus I to the n. Inputting our variables into the equation would yield this result. $33.46, of course, would be our future value, 6% is our I, and 5 is our N. And as you may have guessed, the present value should be equal to $25. We can see here that this is simply the opposite of the compounding scenario that we did when we were talking about future value of a lump sum. Now again, there are various ways to solve this problem. We can use the y to the x key in our as we did in our previous time value of money calculator. We could use the financial calculator. Here we're going to input the variables of future value equal to 33.46, the interest equal to 6, n equal to 5, and we're going to compute our present value. In this case, it's going to give us, the result is going to be a negative $25. Again, remember the notion between inflows and outflows that the calculator must distinguish between. If you're depositing money into an account in one period, you must be withdrawing it out in a future time period, or vice versa. We could use the present value interest factor tables. These are located in the same spot as the future value interest tables that we discussed. And what they do for us is calculate the interest factor component, that is 1 over 1 plus I to the n, which is the present value interest factor for a particular I and an n. So in this case, with our 6% and our 5 for the number of compounding periods, our interest factor would be equal to 0.7473. This we could multiply by the future value and come up with the resulting $25 as we anticipate. The fourth would be an Excel spreadsheet. Again, I have listed in here what the inputs would be, the field inputs would be, future value, I and N, and what the formula underneath the result there would look like. Let's turn now to annuities. Annuities are a series of equal dollar amounts being paid or received at equal points in time, that is, at regular intervals. We're going to be discussing ordinary annuities, that is, that the payment occurs at the end of each period. The annuity begins one period prior to the first payment. So here we've got marked at time 0, we've marked the start of the annuity. And at the point that's marked with a 1 is when the first payment is made. Again, notice that the payment itself occurs at the end of the first period. This is the designation of an ordinary annuity. Now the question we want to answer is we're going to start with present value, and we want to answer the question, what is the value of this series of payments, these equal dollar payments that are equally spaced apart and last for some n number of periods? What is their value at the start of the annuity, marked by the number 0? Well, if we wanted to find the present value of this annuity, what we would need to do is, using our present value formula that we've already learned, we would need to discount each one of those individual payments that we're designating as R's, discount each one of those the appropriate number of periods to get them back to time 0, and then add them all up. Okay, we can see that in this formula where we have added up the discounted value of each individual payment. Now, we might want to try to reduce this equation because, as you can imagine, as we get to large numbers of payments, this formula is going to get rather complicated to solve. Well, let's start by some algebraic manipulation. We know that all of the values in the numerator of each of these terms are equal. They must be in order for an annuity to exist. The annuity, remember, is equal dollar payments equally spaced apart. So if these values in the numerator are different, then we cannot classify this as an annuity. So we know that all of the R's, all of our payments here, are the same value. So let's pull that out of the equation. And that would leave us with the individual interest factors for each term in the equation. Now, through some calculus manipulation, we can take this series that we have in brackets, this is a geometric expansion, and we can reduce it into something that's more manageable. Through a few calculus steps, we would come up with the fact that the present value is equal to the payment, or R, times this term. This is our reduced version of the geometric series that we have in the previous line. In this case, our interest factor would be 1 plus I to the n minus 1 divided by I times 1 plus I to the n. This is what we might call the present value interest factor of an annuity. Now again, we have several ways to solve this particular interest factor. Again, we're terming this term in brackets the present value interest factor of an annuity. It is the interest factor that is applicable to present value of annuity calculations. One way to solve this is to look at the present value interest factor of an annuity tables. Here we have PVIFA representing that present value interest factor of an annuity. We have tables that designate for particular I's and N's what the interest factor is. We can use that interest factor, multiply it by the payment, and we would know for that particular example what the present value of the annuity is. I like to use a representation for this interest factor. Sometimes it's a bit cumbersome to write this all out. So we could represent this interest factor using the notation PVIFA. The thing is we need to make sure that we designate what interest rate and what n we might be using for that interest factor, because of course, as you can see, those are the two variables that would change the value of that interest factor. We can also use an Excel spreadsheet. So let's take a look at an example and then employ some of the various ways to solve. Our example asks, what is the present value of a 10-year annuity with a payment of $50 every 6 months, or $50 every period, where the interest rate is equal to 6% compounded semi-annually? The timeline here represents the actions we are trying to achieve. That is, finding the present value of a 20-period cash flow stream where the payment is equal to $50 each period. We are bringing each $50 payment back to the present, or back to time 0. Let's take a look at the mathematical setup of how we would achieve this, solving this problem. What we're trying to calculate is the present value of each of those $50 payments. If we were to discount each of those individually, we might have a formula that looks like this, where each individual $50 payment is discounted the appropriate number of compounding periods, starting with 1, going all the way out to 20. We could condense this into our formula that we derived for calculating the present value of an annuity. Or we could simply abbreviate these formulas by looking at a representation of the present value interest factor of the annuity. Here we represent that with the letters PVIFA, but we must indicate at what interest rate and what the number of compounding periods we are employing in this calculation. Our calculator will help us to solve this. The calculator steps would include inputting the following variables. We would input a 3 for the interest factor. Remember, we use the percentage form in the calculator. We would enter a 50 for the payment, and we would enter 20 for the n. What we're after to solve is the present value. If we calculate that, we would come up with a value of negative $743.87. Keep in mind that negative sign just indicates the direction of flow here. So that if we are receiving $50 inflows along the 20-period time horizon, then that would be equivalent to a $743.87 outflow in time 0. It does not indicate negative dollars, just direction of flow. As we said, we can also use Excel to solve this particular problem. In this case, our related variables are payment, interest, number of periods, and the value that we're solving for is, of course, present value. I've shown here in the yellow box is the solution. In the orange box shows what the Excel formula looks like behind that value. Now let's suppose that we want to do the opposite of discounting of an annuity. Rather, we would like to compound an annuity or find the future value of the annuity. The future value of an annuity takes all of the payments to the nth year or the final period of the annuity, the end of the annuity. Recall that it's still an annuity, so we have equal dollar values equally spaced apart. If we wanted to find the future value of all of these payments in the annuity, we could employ the techniques that we already know. That is taking or finding the future value of each individual payment, or R, for the annuity stream at hand. We could alter this formula by pulling out the common factor of R. As I said, we know that all of those R's, or all of those payments, must be the same. Otherwise, the concept of an annuity does not exist here. If we do that, we're left in the brackets with all of the interest factors for each of the periods from the first period all the way out to the nth period. Using the magic of calculus, we could reduce that expansion that is denoted in the brackets, and the result would be what we have here, that the future value would be equal to the payment, or R, multiplied by the interest factor. In this case, the interest factor is equal to 1 plus I to the n minus 1 divided by I. As before, we have several ways that we can solve this. We can use the interest factor that we just found, the equation, the future value interest factor of an annuity. We can do this by looking at the tables. We can look in the mathematical tables for the future value interest factor of an annuity and look across and down for the particular I and N associated with the problem. We can use a representation of the formula above, as we did with the present value. In this case, it would be the future value interest factor of an annuity, of course denoting the particular I and N that is relevant to that interest factor. And of course, our calculator we would need to help us with that solution. We could also use an Excel spreadsheet. Let's take a look at an example and then employ the various ways to solve. This example is the same as we had in the present value of an annuity example, only we're doing just the opposite. Instead of discounting back to time 0, rather we are compounding out to time 20, or the end of the annuity. Again, recall when the beginning of the annuity was. It's marked by the variable 0, or the number 0, and the end of the annuity is marked in this case by the number 20. So our example is, what is the future value of a 10-year annuity with a payment of $50 every 6 months, or $50 every period, where the interest rate is equal to 6% compounded semi-annually? Our mathematical setup can be done in several ways. First, we could find the individual future values of each individual payment, or the future value of each lump sum, and add them all together. We could employ the derived formula that we just found for a future value of an annuity using the future value of an annuity interest factor, inserting the appropriate I and N, in this case 3 and 20 respectively. Or we could use the abbreviation, the representation of the interest factor. In this case, we would find the future value by multiplying the payment of $50 by this future value interest factor of an annuity, FVIFA, where we have denoted what the appropriate interest rate is and the number of compounding periods. To do so, we could use our calculator, in which case we would enter the variables 3 for the interest, 50 for the payment, 20 for the N, and calculate the future value. In this case, our computation would result in a value of $1,343.52. Again, note the negative sign here, denoting direction of flow. Now, one important factor that we should mention here when calculating any time value of money calculation in our financial calculator, we must clear out all data before we enter the variables. We must clear the time value of money inputs from each time we make a calculation. Otherwise, data from previous problems will be incorporated in the new problem. Now we have another alternative. Since we already calculated what the present value of that 20 period $50 payment annuity was, we could find the future value by taking the future value of the lump sum amount found as the present value. Recall that we found the present value of that 20 period $50 annuity to be $743.87. We could find the future value of the same annuity by taking that lump sum 743.87 and multiplying it by 1.03 to the 20th. This results in the same exact value for the future value of the annuity as we just calculated. And it must be by definition, this is necessarily the case, that the future value of that same annuity is found by finding the future value of the lump sum of its present value. Let's take a look at another future value of an annuity example. Our example here is that a firm wants to amass $10 million to retire a bond issue in 10 years, and it can earn or expects to earn 12% per year. How much do they have to put away each year if their first payment is to be made 1 year from now? On the timeline, we can see pictorially what it is we're trying to accomplish. We see denoted that payments are made starting at the period designated with the number 1, that is at the end of the first period, and being made all the way out till the 10th period. In doing so, we want to accumulate or save $10 million in total by the end of that 10th period. How could we find what that payment amount must be for each period? That is, what is our savings amount for each period so that we can accumulate or save $10 million by the end of the 10th period? Well, let's look at a mathematical setup as we have for our previous examples. We know that 10 million is the future value. We know that's the amount we want to have at the end of the 10-year period. We know that we're going to put some amount, some payment amount, some constant amount away each period, and that it must grow interest and accumulate interest over time so that when all payments are included and all interest on all payments are included, we will have the resulting $10 million that we're interested in. Another way to set this up is to use our future value of an annuity formula that we derived. Again, 10 million is our future value, payment is our unknown, and we have inputted our interest rate and our N in the appropriate spots in our interest factor. We could simply use the simplified version of the future value interest factor formula. That is stating that 10 million is equal to the payment times the future value interest factor at 12% for 12% interest for 10 periods. It would involve inputting the variables into our calculator as follows. The interest would be entered as a 12. The N would be entered as 10. And the future value would be entered as 10 million. Again, don't forget to clear out all data prior to entering these values into your calculator. What we're solving for, what the unknown in this case would be PMT, the payment. In this case, $569,841.64 would be the amount we would need to deposit into an account that earned 12% for the next 10 periods so that we can accumulate $10 million by the end of the 10th period. If we were to look at how this might appear in Excel, we would have something like this. Our inputs, of course, are future value, interest, and N, and our output is payment. You can see the Excel formula that I have included in this cell, in the yellow cell, has the following behind it. The formula behind it is what is denoted here in the orange box. That is, the payment is times the, or I should say in parentheses, the rate needs to be denoted, the number of periods, The future value, we don't have a present value here, so there's no value there. And our type, of course, is end of period, and that's always defaulted. Okay, now let's take a turn and look at something called the present value of a perpetuity. The question we want to ask here is, what if the payment continued indefinitely? Preferred stock, for example, pays a constant dividend forever. So how do we find what that stream is worth in today's dollars? Let's present an example to help us learn how to do this. What is the present value of a $20 perpetual stream of cash flows if the interest rate is 10%? Well, let's look at that graphically. What our cash flows would look like is a continuous timeline that would continue forever, and we would have $20 cash flows occurring every period. What we want to do is bring all of those cash flows back to the present, back to time zero, and find their value. So how are we going to find an infinite stream of cash flows, or find the present value of an infinite stream of cash flows? Well, let's start out with our present value of an annuity formula. After all, a perpetuity is still an annuity. It still fits the criteria, equal dollar payments equally spaced apart. But it's a special case of an annuity where the n goes to infinity. So we can look at either the long mathematical formula that we've learned when we were calculating annuities and just continue that on indefinitely, or we can look at the condensed version written here. What we need to think about is when n goes to infinity, what will be the impact on these equations? Well, let's start over here on the next slide with rewriting our condensed version of the formula. And then what we're going to do is we're going to mathematically manipulate this formula so that we can see what happens as we have an infinite n, an n that goes to infinity. First thing I'm going to do is split apart the terms in the numerator of this formula. So I have my common denominator that I write for both terms, and splitting out those two terms in the numerator, 1 plus I to the n and 1. I haven't changed this formula mathematically in any way, I've just simply expanded it. Now, what I can see here is that I could eliminate or reduce one side of this formula by crossing out the 1 plus I to the n, since it's common in both the numerator and the denominator of that particular term. Now, that leaves me with a formula that looks like this, that the interest factor is now reduced to this term 1 minus I minus 1 over I times 1 plus I to the n. Now remember, what we're doing here is we're trying to think of the situation where n goes to infinity. So we're actually going to do some calculus and think about that, taking a limit of this particular function as n goes to infinity. What we would see is that as n goes to infinity in this particular formula, that the term in the denominator would get larger and larger as n goes to infinity. The whole term, that is 1 divided by I times 1 plus I to the n, would go to 0 as n goes to infinity. So what we're left with then is that the present value of a perpetuity can be reduced to the formula we have written here. That is, the present value is equal to R times 1 over I. Now, what I like to do is to rewrite that to use the terminology we are accustomed to for an annuity, that is using the PMT. And we would see then that the present value is equal to payment over I. So for the example we started with, where the payment was equal to 20 and the interest was equal to 10%, if we plug in those values into our formula, we would see that the present value of the perpetuity is $200. So that we can say the present value of an infinite stream of $20 cash flows is equal to 200. And that finalizes our review of time value of money. In summary, we presented the present value and the future value of a lump sum, the present value and future value of an annuity, the present value of a perpetuity. These are the 5 main time value of money operators.